All right, this one's going to need a little background before we get into the details, but as it turns out, I have seriously misjudged Jeren, and this video will go through what's happened between us over the last few weeks. All right, so it began over a month ago when I had my debate against Nicholas Quinn over on Jeren's channel. One of three questions to Nick was to make a prediction for the angle you would measure to a mountain that was 30 miles away if the Earth was a globe. And I tried to make it as easy as possible. So both the observer and the distant mountain were at the same elevation, and I didn't even expect him to account for refraction. So all Nick had to do was calculate how much drop there would be on a globe at 8 inches per mile squared, and then draw a little triangle, do some very simple high school trig, and give me the predicted angle. So if you're playing along at home, that's 30 miles times 30 miles equals 900. And then 8 inches is obviously 2/3 of a foot. So the amount of drop is 600 feet. So your triangle has a 600-foot opposite side and a 30-mile adjacent, which is 158,400 feet. And if you take the arctangent of that ratio, you get an angle of 0.217 degrees. But as you can see, Nick is a typical flat earther that has absolutely no clue when it comes to geometry. And despite having the question 3 days in advance, he didn't even ask a Glober friend to do his homework for him. And he just blurted out an utterly ridiculous answer of 30 to 40 degrees. All right, so following the debate, I had a bit of a chat to Jeren on Telegram, and here are a few messages from that chat. I originally started the conversation showing him a measurement of spherical excess. So he goes, well, then you just proved to me that spherical excess is another application of perspective, things lower in the distance. And I agree with that. You know, the classic example of the streetlights, the streetlights are above you and they go down. But then I said, and things below your eye level rise up, right? And he said, yes, they ramp up. And I said, to eye level, right? And he goes, no, not exactly. And I said, why not? Is there some downward bias to perspective? Things above your eye level ramp down towards eye level, I agree. But when I say things below your eye level ramp up to eye level, you aren't so sure. So I'll ask again, is there some kind of downward bias to perspective? And then I followed that up with this set of photos, and I said, I'm at 14 meters, and I point my auto level at a container ship on the horizon where the hull is obstructed, and the whole ship is below the crosshairs. Why did the top of that ship ramp down to below eye level, and the bottom of the ship not ramp up to above eye level? Sounds very downward biasy. And this is where the fun began. Jeren goes, the hell is this? Not even the same boat. The boat on the horizon is white. And I respond with, so is the top of the boat I posted. It's obviously obstructed. And I was just flabbergasted. Jeren just couldn't fathom that what we were looking at was just the very tippy top of that container ship where most of it was hidden by the horizon. All right, so let's spend a few minutes where I go through how I verified my observer height for that photo and how I verified that what I was looking at was the ship that I thought I was looking at. All right, so this observation was actually almost 4 years ago, back in February 2020, and I was up the coast just north of Newcastle, which is a pretty busy shipping port, and had a few hours to kill, so I thought I'd have a look for some boats. My coordinates are at the bottom here, and on Google Earth it says I was at 7 meters elevation, but when I got up there it felt a lot higher than that, so I spent a little bit of time coming up with a plan to make sure of my elevation. Lucky for me, there was a permanent benchmark just up the road that I could use to figure out my elevation over on the headland. Now normally when you do differential leveling you need 2 people, one to look through the auto level and one to hold the measuring rod. I was by myself that day, and when you're by yourself, you kind of have to improvise a little. So there was a power pole in between the benchmark and my observation spot, So it was kind enough to hold the rod for me without too much trouble. All right, here's just a view from Google Street View of the location. Here is the benchmark. You've got to lift up that plate and there's a little silver spike in the ground. And here is the power pole. Now obviously this was 4 years ago and the only thing I recorded against the observation was that it was at 14 meters. So a few of the numbers here are just going to be made up. All I'm really showing you here is the process to get that 14 meters observer height. So first shot, I set up my auto level over the benchmark up the road, stuck the rod up against the power pole and took a reading on the rod. Now my auto level was set up at about 1.8 meters above the benchmark and the benchmark was 12.6 meters, which means my auto level was at 14.4 meters elevation. And let's say the reading on the rod was 2.6 meters. If I subtract that from the elevation of the auto level, that means that the elevation at the base of the power pole, so down here, is 11.8 meters. So then I stuck the rod on the other side of the power pole and went and set up the auto level over on the headland and made another shot back to the measuring rod. Now again, I'm making these numbers up, but let's say the reading on the rod was 2.2 meters. I just add that back onto the elevation of the base of the power pole and I get my elevation of 14 meters. So that's how it was done. All right, but we can also verify that observer height with the photo itself. All right, so inside an auto level, you'll see these two stadia marks and the angular distance between those stadia marks is set at 10 milliradians. So if this distance here is 10 milliradians, I can scale that distance against this line between the crosshairs and the horizon, and I get a horizon dip angle of 1.9 milliradians. I convert that to degrees and I get 0.108 or 6.5 minutes of arc. Now Celestial Navigation has a formula for dip correction, which is the angle down to the horizon. So its dip in minutes of arc is equal to 0.97 times the square root of the observer's height in feet. And I can use that formula to sort of reverse engineer a observer height. So the height of the observer is equal to the dip in minutes of arc divided by 0.97 all squared. And that comes out at 44.9 feet or 13.7 meters. And I was happy with that. Now, here's the ship. It's called Poro Nupuri Maru, and in the marine traffic app, it will give you its latitude and longitude. It will also tell you how far it is from you and in what direction. So I have to be looking at 181 degrees azimuth, which is almost directly south. But how do I know what direction the auto level is pointing in? All right, so this is one of my auto levels. And you can see where that green arrow is pointing, that there's a little window with a number on it. And guess what? That number goes from 0 to 360, which just so happens to match the number of degrees in a full circle. So if I want to know what direction my auto level is pointing, I need to calibrate that azimuth. And the way I do that is to use a landmark with a known azimuth from my location. So all I do is line up the sights of the auto level with that landmark, and then I rotate this black ring until the number matches the azimuth of the landmark, and voila, I can now point the auto level at whatever azimuth a given ship happens to be at. And for this observation, I picked out a big water tower up on the hill, and here it is in some drone footage that I found. And here it is in Google Earth, which gives an azimuth to it of about 315 degrees. So when marine traffic tells me where I need to point my auto level to see the ship, and I point my auto level in that direction, and I see a ship, then I'm pretty sure I've correctly identified the ship. All right, but now let's try and plug things into a curve calculator. But before we do that, we need to get an approximate height of the ship. So here's a photo of the ship from marine traffic. Marine traffic gives the length of the ship as 235 meters. And again, just do some simple scaling to work out an approximate height from the water level up to the top of the red funnel of about 31 meters. Again, that's approximate. And what does the curve calculator say? So the distance away, 32.58 kilometers, and obviously my viewer height is 14 meters, gives a refracted hidden of 22.17 meters. And I don't know about you, but it sure looks to me like about 2/3 of that ship is hidden by the horizon. And now it's crunch time. So, Jeren, up until a few days ago, I actually thought you were one of the rare flirfs that had some intellectual integrity. I mean, I haven't had a huge amount of interaction with you, so I'm more going off your interactions with people like MC Toon a few months back. But overall, I thought you came across as pretty honest. But you seem to have dug your heels in on something very stupid, like not being able to even conceive that my photo is a photo of the ship I say it is, and the majority of it is obstructed bottom up. So, 2 questions are on the screen. Let's see if you can give straight answers.